Year 40 begins with a braking burn. For most of the voyage, the destination has been little more than a point of light fixed ahead of the ship. Now that point is separated into a star, a moving field of planets, and a set of trajectories that must be handled without help from Earth. The crew has crossed more than 4 light years. The propulsion system has worked. The navigation solution is intact. The hull still holds pressure. By the usual language of engineering, the starship has succeeded. Then, the ship creates gravity. Perhaps a rotating habitat has been turning throughout the voyage. Perhaps the crew has spent part of the journey in weightlessness and must now prepare for a landing environment. Either way, arrival requires bodies that can tolerate load, hearts that can maintain blood flow to the brain, eyes that can focus, hands that can perform precise work, immune systems that can control infection, and minds that can make decisions after decades of isolation and radiation exposure. The first critical test may not be whether the engines restart. It may be whether the crew can stand. That changes the meaning of an interstellar mission. Reaching another star is not enough. A functioning spacecraft carrying a medically broken crew has not completed the journey in any useful sense. The people must arrive able to operate the vehicle, respond to emergencies, conduct science, and survive whatever comes next. The mission is therefore not only a contest against distance, it is a contest against the gradual loss of human capability, and gradual loss is difficult to see. Machines often advertise failure. A pump stops, a circuit opens, a temperature rises beyond its limit. Human biology is less cooperative. Bone can weaken while a person feels normal. Cardiovascular reserve can decline while resting measurements still appear acceptable. Vision can change slowly enough that the brain adapts around it. Sleep loss can alter judgment before the exhausted person recognizes how impaired that judgment has become. Immune regulation can shift without producing an immediate illness. Radiation damage can accumulate in cells for years before any single consequence becomes obvious. On Earth, these changes are buffered by a medical system and an environment that continuously support the body. Gravity loads the skeleton and muscles. The atmosphere and magnetic field reduce radiation exposure. Hospitals replace failed organs, remove tumors, treat infections, repair fractures, and replenish medications. Social life provides novelty, privacy, relationships, and escape from conflict. A person can be unhealthy in one system while the rest of the world compensates. A starship removes most of that compensation. The crew takes its habitat, pharmacy, diagnostic equipment, spare parts, food system, and medical knowledge at departure. From that point forward, every resource is finite or must be regenerated. Every treatment competes with mass, power, storage, and maintenance. Every serious illness becomes an engineering event. Every engineering failure becomes a medical event. Distance turns small weaknesses into permanent conditions because rescue, evacuation, and real-time consultation disappear. That is why asking what fails first is more useful than listing everything space can do to the body. The answer may not be a single organ. The first decisive failure could be a relationship between systems. A weakened skeleton becomes more dangerous when muscle has also declined. A reduced cardiovascular reserve matters more when a crew member is dehydrated or ill. Sleep disruption becomes an operational hazard when radiation, age, and confinement have already reduced cognitive flexibility. An infection becomes harder to control when immune function is altered and the most effective drug has degraded in storage. The mission can lose not because one system reaches zero, but because several systems lose enough reserve that none can protect the others. This is a failure cascade. It begins with adaptation. The human body is not simply damaged by space. It also changes itself to function in space. In reduced gravity, tissues that once supported body weight receive less mechanical demand. Fluids redistribute. The heart works under a different pressure pattern. Sensory systems relearn which signals indicate orientation. Metabolism, immune signaling, and gene activity adjust to a new environment. Many of these responses are logical. Maintaining bone and muscle is energetically expensive. If the body detects that heavy supporting tissue is no longer required, it reduces the investment. If blood no longer has to be pushed upward against gravity, the cardiovascular system adapts to the easier task. The problem appears when the mission later demands the old capability again. Biology has optimized itself for the voyage and may no longer be prepared for arrival. Current evidence gives us only a narrow view of that process. Human spaceflight has produced detailed observations across missions lasting days, months, and in a few cases roughly a year or longer. Those missions have revealed losses in weight-bearing bone, muscle deconditioning, reduced aerobic capacity, altered fluid regulation, changes in vision, disturbed sleep, immune shifts, and molecular responses across many tissues. Some changes improve after return to Earth. Others recover incompletely or vary sharply between individuals. But a 40-year mission is not a longer version of a 6-month mission in any simple sense. If a measured change continues for 6 months, it does not automatically continue at the same rate for 40 years. Some processes may level off. Others may accelerate as aging, radiation, confinement, and accumulated disease begin interacting. Countermeasures may work well at first and lose effectiveness later. Individual variation that is manageable in a short mission may become decisive over decades. The honest position is not that we know exactly what a human body would look like after 40 years between stars. We do not. The honest position is that every direct observation ends near the beginning of the timeline we are trying to understand. NASA's Human Research Framework groups the major hazards of exploration into radiation, isolation, and confinement, distance from Earth, altered gravity, and closed or hostile environments. These categories are useful, but a real crew would never experience them separately. The body exposed to altered gravity is the same body receiving radiation. The mind living in confinement is the same mind making medical decisions without immediate support. The aging crew is the same crew depending on equipment and medications that are aging with them. The danger lies in the intersections. Consider the simplest possible timeline. At departure, the crew is selected for exceptional health. Exercise begins immediately. Lighting schedules are controlled. Nutrition is measured. Radiation shelters are available for major solar events. Medical monitoring is constant. The ship may provide partial or full artificial gravity. Every system has redundancy. Even under that favorable design, the mission begins spending biological margin from the first day. Exercise equipment must function for decades. Bearings wear, sensors drift, replacement parts are consumed. A crew member with an injury may be unable to maintain the loading needed to protect bone and muscle. Artificial gravity, if provided by rotation, introduces structural mass and mechanical systems that must remain reliable. Shielding protects against some radiation but adds weight, and high-energy particles are not stopped by simply surrounding the crew with a thin metal wall. More medical capability means more mass, more power, more training, more sterile supplies, and more components that can fail. Every solution changes the vehicle. Every change in the vehicle changes the propulsion requirement. And every reduction in mass, power, redundancy, or shielding changes the risk carried by the crew. This is the central contradiction of the voyage. The ship must protect human biology from interstellar space, but the systems needed to provide that protection make the ship harder to accelerate, harder to maintain, and more dependent on machinery that must survive as long as the people do. So the first chapter of a 40-year mission does not begin with a disease. It begins with a budget of resilience. The crew launches with strong bones, healthy hearts, clear vision, trained judgment, functioning immune systems, and a medical inventory designed around anticipated needs. The question is how quickly that reserve is spent. How much can be restored on board, and which losses make the next losses more likely? Somewhere between departure and arrival, the mission may cross a threshold that an instrument. The crew may still be alive, the ship may still be moving. Every major system may still report nominal operation, but the combined ability to recover from the next fracture, infection, radiation event, equipment failure, or psychological crisis may already be gone. To find what fails first, we have to follow that reserve from the day the engines ignite. The first weeks of the voyage may feel deceptively successful. The engines have completed their initial work. The crew settles into routines. Equipment is checked, meals are scheduled, experiments begin, and the destination remains too distant to look different from any other star. Inside the habitat, almost everything appears controlled. But the body has already noticed that Earth is gone. Gravity is more than the force that keeps a person on the floor. It is a continuous instruction delivered to nearly every tissue in the body. The skeleton receives it through compression and bending. Muscles receive it through the effort required to maintain posture and move weight. Blood vessels receive it through the pressure gradient between the heart, brain, and legs. The balance organs of the inner ear receive it as a fixed reference for direction. On Earth, that instruction never stops. It continues while a person walks, sits, sleeps, or stands still. Remove it, and the body does not preserve every Earth-adapted capability out of loyalty to the planet it left behind. It begins reorganizing itself around the environment it now occupies. The earliest changes are not necessarily failures. They are adaptations. Fluids that gravity normally draws toward the lower body shift toward the chest and head. The face may appear fuller, the legs may become thinner. Pressure sensors near the heart interpret the increased central fluid as evidence that the body is carrying too much volume. Hormonal signals change. The kidneys remove more water and sodium. Plasma volume falls. Within days, the cardiovascular system is operating with less circulating fluid than it carried on Earth. In weightlessness, this can work. The heart no longer has to maintain the same pressure differences required to supply the brain while standing upright. Blood is not constantly pooling in the legs. The reduced volume is sufficient for the new environment. The danger is stored for later. If the crew must suddenly enter a gravitational field, blood will again be pulled downward. A cardiovascular system adapted to weightlessness may struggle to maintain pressure at the brain. The result can be dizziness, weakness, impaired coordination, or fainting at the exact moment the crew needs to perform demanding operations. On a station orbiting Earth, returning astronauts can be met by recovery teams. They can be helped from the capsule, examined by physicians, and guided through rehabilitation. An interstellar crew approaching an unexplored planet would have no such assistance. The people performing the landing would also be the people experiencing the gravitational transition. The mission might demand precision at the moment their bodies are least capable of providing it. Muscle follows a similar pattern. On Earth, the muscles of the calves, thighs, hips, back, and abdomen perform low-level work almost continuously. They stabilize joints, control balance, and prevent the body from collapsing under its own weight. Much of this effort is so familiar that it never enters conscious awareness. In weightlessness, the same tissue becomes expensive material with less work to do. Muscle fibers shrink. Strength and endurance can decline. The muscles most responsible for posture and locomotion are particularly vulnerable because the tasks that normally activate them have nearly disappeared. Even the nervous system changes how it recruits muscle, adapting movement to a place where a light push can send the body across a room. Modern exercise systems can reduce these losses significantly. Astronauts aboard the International Space Station follow carefully prescribed programs that combine resistance and aerobic training. With reliable equipment, sufficient nutrition, and strict adherence, many crew members return with relatively limited average losses in muscle size and strength. That is an important success. It is not evidence that the problem has been solved for 40 years. A station exercise program depends on large machines, trained ground teams, replacement components, medical monitoring, and a mission duration measured in months. On an interstellar ship, the equipment must operate across decades. Cables fatigue, bearings wear, seals degrade, sensors lose calibration, lubricants migrate or break down, software and control electronics require repair. Every hour spent maintaining the exercise system is an hour not spent maintaining something else. The crew must also remain healthy enough to use it. A knee injury, spinal problem, infection, or fracture could interrupt training for weeks. On Earth, temporary inactivity is followed by rehabilitation in normal gravity. In weightlessness, inactivity removes one of the few remaining mechanical signals protecting the body. The person most in need of exercise may become the person least able to perform it. Bone responds more slowly than muscle, but its loss may be more difficult to reverse. Bone is living tissue. Specialized cells continually remove older material while others build new structure. Mechanical loading helps regulate that balance. When weight-bearing bones no longer carry weight, the signals supporting bone formation weaken. Without effective countermeasures, density in regions such as the hips, spine, and legs can decline rapidly compared with ordinary aging on Earth. Current resistance exercise has improved outcomes, but astronauts still show substantial individual variation. Some lose more than others. Changes in bone mineral density do not capture the entire risk, because bone strength also depends on internal architecture, geometry, and the distribution of material. A scan can show how much mineral remains, without fully revealing how well the structure will tolerate an unusual impact years later. Calcium released during bone breakdown does not simply disappear. It enters the bloodstream, passes through the kidneys, and can contribute to conditions that create their own operational risks. A system that begins with reduced mechanical loading can eventually affect renal health, fracture probability, exercise capacity, and the crew's ability to recover from injury. The cascade has already started. Suppose a crew member loses bone strength despite years of training. Later, declining vision or a moment of disorientation causes a collision during maintenance. The impact produces a fracture that a healthier skeleton might have tolerated. The fracture prevents resistance exercise. Muscle and cardiovascular fitness decline during recovery. Pain disrupts sleep. Reduced mobility increases dependence on other crew members. Medical supplies are consumed. A single injury becomes a mission-wide loss of labor and reserve. Nothing in that sequence requires an immediate catastrophic event. Each step is manageable by itself. The danger appears in the connections. Artificial gravity is the most direct attempt to stop the process at its source. Rotate a habitat, and the crew experiences acceleration toward its outer wall. With an appropriate radius and rotation rate, the floor can load the skeleton, require muscles to support body weight, and re-establish a cardiovascular pressure gradient. Instead of asking exercise and medication to imitate selected effects of Earth, the ship recreates part of the condition that produced those effects. The physics is straightforward, the engineering is not. A small habitat must rotate quickly to generate useful acceleration. Rapid rotation can create uncomfortable differences between the forces at the head and feet. Movements across the rotating frame produce Coriolis effects that may cause disorientation, nausea, and difficulty coordinating motion. A larger radius allows slower rotation and a more uniform experience, but the larger structure requires more material. That material must be launched, assembled, accelerated, protected, and maintained. A rotating habitat also creates structural loads that continue for the life of the mission. Joints, bearings, pressure seals, and rotating interfaces must survive billions of cycles. If the propulsion system is attached to a non-rotating section, people, power, fluids, data, and cargo must move between rotating and stationary structures. Each interface becomes another possible failure point. The solution to biological deconditioning therefore increases spacecraft mass and mechanical complexity. Increased mass demands more propulsion energy. More machinery demands more spare parts. More spare parts add still more mass. Reducing the radius makes the ship easier to build, but may make the gravity less tolerable. Reducing the gravity lowers structural demand, but may not provide enough biological protection. Operating the system only part of each day saves some resources, but raises a question no long-duration human mission has answered. How much gravity, at what strength, and for how many hours, is enough to preserve a healthy body across decades? We do not know whether lunar gravity is sufficient. We do not know whether Martian gravity prevents the major changes seen in weightlessness. We do not know whether short daily exposures to higher gravity can replace continuous lower gravity. Human beings have lived for months in microgravity and for days in lunar gravity. No one has lived for years in the broad range between them. A starship designer must therefore choose a gravity prescription before the necessary human evidence exists. Full Earth gravity may provide the strongest biological confidence, but impose the greatest structural and propulsion cost. Partial gravity may be more practical, but leaves slow losses that only become visible after the ship is committed. Intermittent centrifugation may reduce some risks while failing to protect other systems. The crew could spend the first decade feeling healthy, passing routine tests, and completing every exercise session, while a structural deficit develops too slowly for the mission to recognize its final significance. By the time the destination is close enough to matter, the experiment has already lasted 40 years, and gravity is only the first environmental protection the ship must recreate. Even a perfect rotating habitat could load the skeleton, train the heart, and pull fluid away from the head while doing almost nothing about the particles passing through its walls. The crew may solve the problem of standing and still lose the ability to think clearly enough to land. The radiation clock starts before the crew notices anything. There is no flash when the ship leaves the stronger protection of Earth. No visible line marks the edge of safety. The cabin lights remain steady. The air feels the same. The crew may be sleeping when the radiation environment changes from one shaped by a planet to one shaped by the sun, the galaxy, and the material of the spacecraft itself. That last part matters. Space radiation is not a single substance moving through an empty corridor. It is a population of particles with different energies, charges, origins, and biological effects. Some come from the sun during energetic eruptions. Others arrive from outside the solar system after being accelerated to enormous energies by violent astrophysical processes. These galactic cosmic rays include protons and the nuclei of heavier atoms moving fast enough to pass through a spacecraft, through tissue, and sometimes through the entire body. On Earth, the atmosphere and magnetic field reduce this exposure. A starship has neither unless it carries an artificial substitute. The most dramatic threat comes from a major solar particle event. A powerful eruption can send large numbers of energetic protons outward through the solar system. If the ship is in their path, exposure can rise quickly. This is the kind of danger that rewards forecasting, alarms, and a protected shelter. The crew might retreat into a compact compartment surrounded by water tanks, food stores, fuel, equipment, or other hydrogen-rich material already carried for the mission. Mission planners can arrange those supplies so that mass serving one purpose also provides protection. The shelter does not need to make the event harmless. It needs to reduce the dose enough to prevent acute illness and preserve the crew's ability to operate. For a solar storm, mass can be highly effective, but solar storms are intermittent. Galactic cosmic rays are persistent. They arrive from many directions. Their highest energy components are difficult to stop, and the heavy nuclei among them can deposit concentrated tracks of ionization as they pass through cells. They can break molecular bonds directly or create reactive chemistry around their path. DNA damage is not unusual in ordinary life. Cells repair it constantly. The concern in deep space is the quality, frequency, and distribution of damage produced by particles that terrestrial biology rarely encounters at the same intensity. Some cells repair the damage correctly. Some die. Some survive with mutations. Over enough time, those outcomes alter the probability of cancer, degenerative disease, and other effects. The crew will not feel most of this happening. A cell does not announce that one chromosome has been misrepaired. A blood vessel does not report the first microscopic injury that may contribute to disease years later. A neuron crossed by an energetic particle does not produce a warning light. Radiation is dangerous, partly because the biological record accumulates long before the mission knows what the final consequence will be. This makes radiation fundamentally different from many engineering failures. A damaged component can sometimes be isolated, replaced, or rebuilt. A damaged tissue is a distributed system. The body may compensate for years, and by the time symptoms appear, the initiating event may be far in the past. A 40-year voyage transforms probability into mission architecture. Even if the risk during any single day is small, the exposure continues through thousands of days. The crew also ages while the dose accumulates. Their repair systems, immune surveillance, cardiovascular health, and reserve capacity do not remain fixed at launch values. Radiation, therefore, does not act on the same biological target for 40 years. It acts on a body that is changing for other reasons at the same time. This is where the question of what fails first becomes difficult. Cancer is an obvious concern, but it may not be the first operational consequence. Radiation research also examines possible effects on the cardiovascular system, the central nervous system, the lens of the eye, and other tissues. The exact magnitude of many deep space risks remains uncertain because no human population has experienced the full mixture of galactic cosmic rays across anything close to an interstellar mission duration. Ground experiments can reproduce selected particles and energies. Animal and cellular studies can reveal mechanisms. Computer models can estimate transport through shielding and tissue. Astronaut records can show effects from shorter exposures. None of these is identical to observing a human crew for decades beyond Earth. The uncertainty does not mean the risk is imaginary. It means the mission would be committing people before the response curve is known. The central nervous system is difficult to evaluate. Animal studies using simulated components of space radiation have reported changes in cognition, behavior, inflammation, and neural structure under some exposure conditions. These findings cannot be translated directly into a precise prediction for human astronauts. Species differ. Doses may be delivered over different time patterns. A laboratory beam cannot reproduce every feature of the interplanetary environment, but the mechanism is plausible enough to demand attention. A crew does not need to develop severe neurological disease for the mission to be affected. Small declines in attention, working memory, cognitive flexibility, or decision quality could matter in a system where mistakes propagate. The ship may operate normally for years, with human performance only slightly reduced. Then, an unfamiliar failure appears, several alarms conflict, and the crew must identify which instrument is wrong before a corrective action makes the situation worse. The difference between success and loss may be a judgment made in minutes by a brain exposed for decades. Radiation protection, therefore, becomes a problem of mass, geometry, and uncertainty. The simplest response is more shielding. Place material between the crew and incoming particles. This works well for many lower energy particles and is essential for solar events. Yet galactic cosmic rays make the relationship less intuitive. When a high-energy nucleus strikes shielding, it can fragment. The collision may produce neutrons, protons, lighter nuclei, and other secondary particles that continue into the habitat. Shielding can reduce one part of the radiation field while creating another. The material still matters. Hydrogen-rich substances are often useful because their light nuclei can reduce some secondary particle production compared with heavier structural metals. Water, polyethylene, food, and waste can all be arranged as part of the protective design. But no practical layer turns a decades-long interstellar cabin into the radiation environment of Earth's surface. More shielding also means more mass. More mass demands more energy to accelerate and decelerate. It enlarges the propulsion system, increases structural requirements, and may lengthen the voyage if performance is limited. A longer voyage produces more cumulative exposure, consumes more supplies, and gives every biological and mechanical system more time to decline. Protection against radiation can therefore increase the time spent in radiation. The trade-off is not a reason to abandon shielding. It is a reason the answer cannot be reduced to adding thicker walls. A starship could place the crew deep inside the vehicle, surrounded by tanks and stores. That geometry may provide strong protection early in the mission when supplies are abundant. As water is consumed, waste processed, fuel depleted, and cargo redistributed, the shielding pattern changes. The safest compartment at launch may not remain the safest in year 30 unless the mass is deliberately preserved or moved. A vessel designed around consumable shielding must treat inventory management as radiation medicine. Active protection has also been proposed. Magnetic or electric fields could, in principle, deflect charged particles before they reach the hull. The concept resembles one function of a planetary magnetosphere, but reproducing that function around a spacecraft is difficult. The system would require powerful fields, large structures, energy, heat rejection, and reliable control across decades. It would also need to protect the crew without creating unacceptable field environments inside the habitat. High-energy particles are not easily persuaded to turn. An active shield that reduces exposure, but depends on complex hardware, creates another vulnerability. If it fails in year 20, the crew cannot recover the dose already received and may not have enough passive protection for the years remaining. A device intended to preserve biological reserve becomes a single system whose long-term reliability helps determine whether that reserve survives. The safest design would combine methods: passive material, protected storm shelters, monitoring, mission timing, operational procedures, possibly pharmaceuticals, and perhaps active systems if they become practical. No single layer would carry the entire burden, but every layer must work with the others. Radiation monitoring must remain calibrated. Forecasting instruments must detect solar activity. The crew must reach shelter quickly. Medical systems must distinguish radiation effects from aging, infection, fatigue, or other causes. Shielding must be maintained as mass moves through the ship. Biological countermeasures must remain safe after years of use. The propulsion plan must carry all of it, and the crew must continue making good decisions about a threat they cannot see. By the end of the first decade, every astronaut may still appear healthy. Tests may show only modest changes. The mission log may contain no radiation emergency at all. Yet the ship will have accumulated something no repair crew can remove: uncertainty inside living tissue. The first system to fail may not be the one receiving the highest dose. It may be the system that depends on every other system remaining precise. Precision begins to erode long before competence disappears. A crew member does not wake one morning unable to operate the ship. The change is quieter. A checklist takes slightly longer. A familiar display requires more concentration. A disagreement that once would have been resolved in minutes stretches across an hour. Someone misses a detail, notices it later, corrects it, and records the event as minor. On Earth, small errors are absorbed by institutions. A second team reviews the calculation. A specialist answers the question. A replacement worker takes over when fatigue becomes obvious. On a starship, the same people carry the same responsibilities for decades. Their judgment is not merely one system among many. It is the system that interprets every other system. That makes cognition a form of infrastructure. The brain depends on conditions. The voyage steadily changes. Sleep becomes less reliable. Light cues are artificial. Social relationships become repetitive. Radiation exposure accumulates. Exercise, maintenance, medical work, and routine operations compete for the same limited attention. Emergencies arrive without the possibility of outside assistance. Even if each stressor produces only a modest effect, the mission is asking the crew to preserve exceptional judgment under conditions that repeatedly erode it. Sleep is one of the first places this pressure becomes visible. Human circadian timing is not a preference for morning or night. It is a coordinated biological system that influences alertness, hormone release, body temperature, metabolism, immune activity, and the timing of cellular repair. On Earth, light resets that system every day. Dawn changes the spectrum and intensity of illumination. Evening reverses the signal. The cycle is reinforced by meals, activity, temperature, and social behavior. A spacecraft has no dawn unless its lighting system creates one. That sounds easy. Lamps can brighten and dim. Their spectrum can shift across the day. Schedules can be programmed around a 24-hour cycle, but artificial timing only works if the crew follows it. The system remains reliable, and mission demands do not repeatedly override it. Emergencies do not respect bedtime. Maintenance windows may require work during the biological night. Scientific observations may be tied to events outside the ship. A medical crisis may keep several crew members awake for 2 days. Interpersonal conflict can disturb sleep long after the conversation ends. Pain, medication, anxiety, and changing age all alter the ability to rest. In the early years, lost sleep can be recovered. In the later years, the pattern may become chronic. Chronic sleep restriction does not merely make people feel tired. It affects attention, reaction time, working memory, emotional control, and the ability to evaluate risk. The most dangerous feature is that subjective confidence can decline more slowly than actual performance. A person may feel adapted to reduced sleep while continuing to make more errors. On a starship, that gap between confidence and capability matters. A tired crew member may still complete routine tasks successfully. Familiar procedures rely partly on habit. The failure appears when the situation is novel, when several signals must be integrated, or when the correct response conflicts with the most obvious one. Those are exactly the conditions likely to define the rare emergencies that determine whether the mission survives. Vision adds another layer. In microgravity, body fluids shift toward the upper torso and head. Some astronauts on long-duration missions have developed changes involving the eye and optic structures, including altered shape and changes in visual acuity. The exact causes remain under investigation, and individual responses vary. What is clear is that spaceflight can change vision in ways that are not explained by ordinary eye strain. A rotating habitat providing sufficient gravity might reduce this problem by restoring a head-to-foot fluid gradient. Partial gravity might reduce it incompletely. Intermittent gravity might help some systems more than others. Without direct decades-long human data, the protective threshold is unknown. Even small changes could become operationally important. Instrument design can compensate for reduced acuity. Displays can use larger symbols. Interfaces can rely more on sound and touch. Automated systems can verify commands. But each compensation assumes the underlying impairment is stable. Progressive change is harder. A display readable in year 10 may be inadequate in year 30. A crew member may adapt to slowly changing vision and fail to recognize how much precision has been lost. The ship itself also ages. Screens dim, optical sensors degrade, camera systems collect radiation damage, lighting becomes less uniform. Replacement parts may not perfectly match the originals. The human visual system and the ship's visual interfaces can decline at the same time. The crew may compensate for each independently and still lose performance because both are moving in the wrong direction together. Balance and orientation present a related problem. On Earth, the brain combines information from the inner ear, vision, muscles, joints, and skin to determine which way is down and how the body is moving. In weightlessness, the constant gravitational reference disappears. The nervous system learns to rely more heavily on vision and other cues. That adaptation is useful during cruise. It may become dangerous during transition. If the ship changes rotation rate, enters partial gravity, begins a landing sequence, or requires movement between rotating and non-rotating sections, the crew must repeatedly reinterpret sensory information. A person who has spent years in one environment may experience disorientation in another even when the new condition is physically safe. The nervous system does not instantly switch operating modes. A maintenance worker moving through a rotating habitat may feel forces that change with direction of motion. Turning the head can create unexpected sensations. Climbing inward toward the rotation axis reduces apparent gravity. Returning outward increases it. If the design is compact enough for these differences to be noticeable, ordinary movement becomes a learned technical skill. After decades, the oldest crew members may be the most experienced and the least physiologically adaptable. Aging changes reaction time, balance, hearing, vision, sleep, and cognitive reserve even in healthy people on Earth. It does not remove competence. In many professions, experience improves judgment long after physical speed begins to decline. But the starship cannot choose between experience and physiology. The people with the deepest knowledge of the vessel are also the people who have spent the longest time exposed to its environment. The mission depends on knowledge that is becoming embodied in aging brains. That creates a risk no replacement component solves. Procedures can be documented. Simulations can preserve technical training. Artificial intelligence may assist diagnosis and decision-making, but a 40-year mission will encounter situations never included in the original model. Materials will fail in unexpected combinations. Biological conditions will appear that no medical database anticipated. Social changes will alter how the crew interprets authority and risk. Automated systems can narrow the problem. They cannot guarantee wisdom. The crew must therefore preserve not only memory but also cognitive flexibility, the ability to abandon a familiar explanation when evidence points elsewhere, to revise plans without panic, and to recognize when the ship's own automated guidance is wrong. Isolation places continuous pressure on that flexibility. The crew may receive messages from Earth, but interstellar communication does not create conversation in the ordinary sense. Early in the voyage, delays are measured in months. Later, a question and response may span years. News from home describes a world that has already changed again by the time the message arrives. The psychological effect is not simply loneliness. It is the loss of shared time. People on Earth continue living in a present the crew cannot join. Families age. Institutions change. Languages, politics, science, and culture move forward. The ship receives fragments of that evolution as historical documents. The crew can answer, but their reply enters another long delay. Relationships become exchanges between different moments rather than interactions inside the same one. Over time, the ship becomes its own social world. That may protect the crew. Shared routines, traditions, celebrations, and a strong sense of purpose can provide structure. But a closed society also concentrates conflict. There is no separate community to enter after an argument. No private life truly independent of the mission. A disagreement between two specialists can become a threat to maintenance, medicine, leadership, and morale at the same time. On Earth, people can leave jobs, relationships, and institutions that become destructive. On a starship, departure is impossible. The crew must solve every conflict inside the same sealed system where it began. This makes social stability part of flight control. A technically brilliant crew can still lose effectiveness if trust declines. Information may be withheld, medical symptoms may be concealed, maintenance concerns may be dismissed because of personal history. Leadership decisions may be interpreted through years of resentment. The hardware continues functioning, but the network of cooperation that gives the hardware meaning becomes unreliable. The first cognitive failure of the mission may therefore belong to no individual. It may be a group losing the ability to form an accurate shared picture of reality. The signs would be subtle: more duplicated work, more unreported mistakes, greater dependence on rigid procedure, less willingness to question a senior crew member, more time spent resolving disputes that once seemed trivial. Each event might appear manageable. Together, they would mean the ship's human decision system is becoming less coherent. By the middle of the voyage, the crew may still be intelligent, trained, and deeply committed. But their sleep is less restorative. Their sensory systems have adapted to an artificial world. Their bodies are older. Their relationships carry decades of history. Their brains have accumulated radiation exposure, stress, and fatigue. The ship has not yet asked them for their hardest decision. It is saving that for the day something breaks. When something breaks, the first question is not whether the crew knows what happened. It is whether the ship still contains what the solution requires. A starship cannot carry a hospital in the way a city contains one. It can carry selected capabilities: imaging systems, surgical tools, pharmaceuticals, laboratory equipment, sterile supplies, rehabilitation devices, and people trained to use them. Every item must justify its mass, volume, power demand, maintenance burden, and shelf life. Every omission becomes a risk accepted before departure. That is manageable when the likely medical problems are known. A 40-year mission changes the calculation because the crew does not remain the population it was at launch. They age. Their exposure history changes. Chronic conditions emerge. Radiation may increase the probability of some diseases. Altered gravity may affect bone, muscle, circulation, vision, and kidney function. Psychological stress may change sleep, adherence, and judgment. A medical inventories for healthy adults in their 30s may become a medical system serving people in their 60s and 70s under conditions no clinical guideline fully describes. The ship must predict not only illness, but the future biology of its own crew. That prediction will be wrong in places. On Earth, medicine is built around depth. A patient enters a system containing specialists, laboratories, blood banks, pharmacies, surgical teams, pathology services, intensive care, and equipment designed for problems that may affect only a small fraction of the population. No single hospital contains every capability, but the larger network provides access. A starship has breadth without depth. It must be prepared for infection, trauma, dental emergencies, kidney stones, fractures, arrhythmias, stroke, cancer, appendicitis, psychiatric crisis, reproductive complications if the mission includes pregnancy, and conditions that have not yet been associated with long-duration spaceflight because no one has remained in space long enough to develop them. It cannot carry a full specialist team for each possibility. The crew may include one physician, perhaps two, with broader medical training distributed among other members. Automated diagnostic systems may provide guidance. Robotic tools may assist procedures. Medical databases can preserve far more knowledge than any individual can memorize. But knowledge is not the same as capability. A database can describe a surgical procedure. It cannot guarantee a sterile operating field, functioning anesthesia equipment, adequate blood products, or a surgeon whose hands have performed the operation before. A diagnostic model can identify a likely cancer. It cannot manufacture a missing drug or replace an imaging component that failed 12 years earlier. The distance from Earth changes consultation itself. Near Earth, telemedicine allows remote specialists to review images, discuss symptoms, and guide procedures. Communication delay may be inconvenient, but expertise can still participate while the case is active. On an interstellar voyage, the delay grows until medical consultation becomes historical correspondence. A crew member develops severe abdominal pain. The ship sends symptoms, images, laboratory results, and its preliminary diagnosis toward Earth. Years later, a response arrives from physicians who have studied the case in detail. By then, the patient has recovered, undergone improvised surgery, or died. The crew is medically autonomous whether the mission planners want it to be or not. That autonomy depends on supplies whose condition changes with time. Pharmaceutical stability is not permanent. Some medications tolerate long storage, well under controlled conditions. Others lose potency, form degradation products, or depend on packaging, temperature, humidity, and radiation protection. Refrigerated drugs add another chain of dependence. Cooling systems, sensors, backup power, seals, pumps, and replacement parts. A medicine that exists on the manifest but no longer contains a reliable dose is not a medical resource. The crew can test potency if the ship carries the right analytical equipment and reference standards. It can rotate stock if the vessel includes pharmaceutical manufacturing. It may be able to synthesize simple compounds from stored precursors or biological systems. Advanced biomanufacturing could eventually produce certain proteins, antibodies, or personalized treatments. But onboard production creates its own demands. Raw materials must be stored or recycled. Sterility must be maintained. Quality must be verified. Contamination must be detected. Complex drugs may require cell cultures or engineered organisms that remain stable over decades. Manufacturing equipment must be repaired by the same crew, depending on the products it makes. The medical system begins to resemble a small industrial ecosystem. Every added capability reduces dependence on stored supplies and increases dependence, machinery, expertise, and energy. Blood is an example. A serious injury or operation may require transfusion. Stored blood products do not remain usable for decades. The crew itself becomes the donor pool, which is small and medically interdependent. Blood types, antibodies, disease status, and the health of potential donors all matter. A crisis affecting several people at once can reduce both the number of available donors and the number of trained clinicians able to manage the transfusion. One accident can consume the mission's medical reserve from both directions. Trauma is especially dangerous because it can occur without warning. A failed restraint during rotation, a collision in a maintenance space, a pressure-related event, or a tool moving unexpectedly can produce injury. A crew with reduced bone strength may fracture more easily. A crew member with altered vision or balance may be more likely to fall. A wound heals in a body whose immune regulation and tissue condition may already be compromised. The accident is not separate from the voyage. It is the voyage expressed through one moment. Kidney stones reveal the same pattern. Bone resorption can increase calcium in the urine. Hydration may be difficult to maintain during illness or heavy workloads. Diet is constrained. Altered fluid regulation changes renal conditions. A stone that would be intensely painful but routinely manageable on Earth can become an operational crisis in deep space. If it passes, the event consumes medication, sleep, attention, and labor. If it does not, the crew may need equipment and procedural expertise that were included for a low-probability event decades earlier. If that equipment has failed, the medical decision becomes an improvisation under pain, fatigue, and time pressure. The first major medical emergency will test more than the medical officer. It will test whether the crew trusts the diagnosis, whether leadership accepts the risk of a procedure, whether the patient consents, whether supplies are preserved for future emergencies, and whether the person making the decision is also a close friend, partner, rival, or essential specialist. In a small crew, medicine cannot be separated from social structure. The engineer requiring surgery may be the only person capable of maintaining the power system. The physician may also be the patient. The commander may overrule a medically necessary period of rest because a propulsion event is approaching. A crew member may conceal symptoms out of fear that being declared unfit will transfer an impossible workload to others. On Earth, medical privacy protects the patient. On a starship, every significant diagnosis may alter the operational future of the entire group. Cancer would create one of the hardest decisions. Radiation exposure, aging, and ordinary lifetime risk make it plausible that a long mission will eventually face a malignancy. Early detection may be possible through regular imaging, molecular screening, or blood-based monitoring. Treatment is harder. Surgery may be feasible for some tumors. Radiation therapy requires specialized equipment and careful planning. Chemotherapy depends on drugs, dosing, supportive care, and management of infection risk. Newer targeted therapies may be highly specific to the molecular features of the tumor and may not be among the treatments loaded decades earlier. A cancer detected in year 30 may belong to a category that was poorly understood when the ship launched. Earth may have developed an effective therapy in the meantime. The crew can receive the instructions. It may not possess the compound, manufacturing pathway, or equipment needed to use them. The mission can know that a cure exists and still be unable to reach it. This is a new form of medical isolation, not ignorance, but separation from capability. The ship's designers may respond by maximizing automation. Surgical robots, diagnostic algorithms, autonomous pharmacies, and continuous monitoring could preserve expertise beyond the limits of the crew. These systems will be essential. They also create a dependency on software and hardware whose failures may be subtle. A diagnostic model trained before launch may perform poorly on biological patterns created by decades in altered gravity and radiation. Sensors may drift. Reference ranges derived from Earth populations may no longer describe the crew. An automated system may interpret space-adapted physiology as disease or dismiss disease because the patient no longer matches its assumptions. The medical system will need to learn during the voyage. Learning systems can adapt. They can also accumulate error. The crew must be capable of challenging their own tools while depending on them. By the middle decades, medicine less about restoring everyone to ideal health and more about preserving enough function for the mission to continue. Chronic conditions may be managed rather than cured. Work roles may be reassigned. Exercise prescriptions may become individual. Drug use may become a negotiation between immediate benefit and limited supply. The definition of acceptable health begins to shift. A person who would receive extensive treatment on Earth may remain at work because no replacement exists. A condition considered disabling in a terrestrial setting may become normal aboard the ship. Pain, reduced vision, limited mobility, or cognitive decline may be absorbed into routine until the crew forgets how much capacity has been lost. That normalization is dangerous. The mission can adapt to decline so successfully that it no longer recognizes the approach of a threshold. Then a second emergency arrives before the first has fully resolved. The physician is exhausted, the pharmacy is depleted, the imaging system is unreliable. Two crew members cannot perform their usual duties. The remaining people work longer hours and sleep less. Maintenance is deferred, exercise is shortened. A medical event begins consuming the protections against the next one. The failure cascade has entered the clinic, and beyond the clinic is a problem no treatment can isolate from the rest of the ship. The crew's immune system is changing, while the spacecraft remains a sealed microbial world. A sealed spacecraft is not sterile. It leaves Earth carrying the crew's skin bacteria, gut microbes, oral communities, dormant viruses, fungal spores, food-associated organisms, and whatever survives cleaning inside equipment, vents, filters, fabrics, and inaccessible joints. Most of these organisms are harmless, many are necessary. Human beings do not travel as isolated bodies. They travel as ecosystems. The ship becomes an ecosystem too. Air moves through the same ducts. Water passes through the same recovery system. Surfaces are touched by the same hands. Food is prepared in the same confined spaces. Waste is processed only meters from living quarters. Microbes shed by one crew member enter an environment shared by everyone else. On Earth, microbial exposure is diluted through enormous spaces and changing populations. A person moves between buildings, outdoors, soil, plants, animals, weather, and communities containing thousands of different biological inputs. On a starship, the microbial world is small, recycled, and repeatedly filtered through the same people. That does not automatically make it dangerous. The danger is that both sides of the relationship change. The microbes adapt to the spacecraft. The crew's immune systems adapt to spaceflight. Cleaning chemicals, radiation, low shear fluid conditions, limited diets, stress, medication, and the closed habitat apply selective pressures over decades. The organisms best suited to survive those pressures become more common. Others disappear. The ship begins evolving with the crew. Immune function in space does not simply switch off. It becomes dysregulated. Some defenses may weaken while inflammatory signals rise. Certain immune cells respond differently to stimulation. Latent viruses carried quietly in the body can reactivate more often under stress. Wound healing and microbial control may change. Individual responses vary, and much of the evidence comes from missions far shorter than the voyage being considered. But the operational problem is clear. A crew member does not need to become profoundly immunocompromised for the mission to be affected. A modest decline in immune surveillance can make ordinary infections last longer, increase viral shedding, complicate recovery from injury, and raise the cost of every medical procedure. In a closed habitat, one person's altered immunity becomes everyone's exposure environment. Many adults carry herpes family viruses in a latent state. These viruses remain inside the body after the initial infection and can reactivate when immune control changes. Reactivation may produce obvious illness, mild symptoms, or no symptoms at all while viral particles are still shed. On Earth, this is common and usually manageable. On a starship, repeated reactivation across a small crew creates persistent biological traffic. The same people encounter the same viruses again and again. If immune function is altered across the entire group, the balance between host and pathogen may shift in ways that short missions have not had time to reveal. The crew cannot replace itself with a healthier population. It must manage the same biological network for 40 years. Bacteria present a different challenge. Some species can form biofilms, organized communities attached to surfaces and protected within a self-produced matrix. Biofilms can develop inside water systems, condensate lines, seals, filters, medical equipment, and areas that are difficult to inspect. A free-floating bacterium may be removed by filtration or killed by disinfectant. A mature biofilm can be far more persistent. Its outer layers alter chemical conditions for organisms deeper inside. Cells exchange signals and genetic material. Some enter slow-growing states that make them less vulnerable to treatments aimed at active metabolism. A surface that appears clean can contain a microbial structure adapted to the ship's specific materials and maintenance routines. Over decades, biofilm control becomes infrastructure maintenance. Filters must be changed. Pipes must be inspected. Water chemistry must remain within narrow limits. Disinfection cannot be so aggressive that it damages equipment, destabilizes the beneficial microbiome, or creates toxic residues. The crew must suppress dangerous growth without attempting to eliminate microbial life entirely. Elimination would be impossible and probably undesirable. The human gut alone contains a dense community involved in digestion, immune regulation, metabolism, and the production of compounds that affect other organs. A spacecraft diet, even if nutritionally complete, may not support that community in the same way as a varied terrestrial diet. Stored foods change over time. Fresh crops, if grown on board, come from a limited agricultural system. Antibiotic use can disrupt microbial balance. Stress and altered sleep can change it further. The gut microbiome may drift. Some changes may be harmless adaptation. Others may affect inflammation, metabolism, or resistance to infection. The problem is not that any departure from an Earth baseline must be corrected. The problem is that the crew may not know which changes are protective and which are early signs of decline. Their bodies are entering a biological state with no established clinical reference. Routine medicine depends on comparison. Blood values, microbial profiles, hormone levels, immune markers, and imaging results are interpreted against ranges derived from populations on Earth. A crew living in artificial gravity, recycled air, controlled light, chronic low-dose radiation, and a closed microbial environment may gradually move outside those ranges. The medical system must decide whether the change represents adaptation or disease. Treat adaptation as disease, and the intervention may cause harm. Treat disease as adaptation, and the crew may lose the chance to stop it. Antibiotics reveal the trade-off sharply. They can save a life, prevent an infection from spreading, and make surgery possible. They also impose strong selection on microbial populations. Repeated use favors resistant organisms, especially in a closed environment where surviving strains remain inside the same habitat. A 40-year voyage cannot assume that the antibiotic sensitivity patterns present at launch will remain unchanged. The ship needs diagnostic tools capable of identifying organisms and testing which drugs still work. It may need the ability to manufacture or modify treatments. It must preserve pharmaceutical compounds and maintain infection control procedures under conditions where fatigue and equipment degradation make perfect compliance unlikely. Even then, resistance may emerge. A resistant infection on Earth can be treated with alternative drugs, specialist care, isolation facilities, and access to new compounds. A resistant infection on a starship is constrained by what the vessel carried, what it can produce, and what remains functional. The microbial threat does not need to come from an exotic space organism. It can emerge from familiar organisms given unfamiliar time. Fungi add another concern. Spores tolerate harsh conditions. Fungal growth can damage materials, contaminate air systems, and create health risks, particularly for people whose immunity is impaired. Moisture control is therefore not only a comfort issue. Condensation behind panels or inside poorly ventilated spaces can create hidden habitats. The spacecraft must monitor places the crew cannot easily see. Sensors may detect humidity, volatile compounds, or changes in airflow. Robotic inspection systems may enter ducts. Materials can be selected to resist growth, yet every hidden cavity becomes a long-term ecological experiment. The same is true of the food system. A decades-long mission cannot rely entirely on food loaded at departure. Even if enough calories could be stored, vitamins degrade, packaging fails, textures and flavors become psychologically oppressive, and mass becomes enormous. Some form of onboard agriculture or biological food production is likely, that introduces soil substitutes, nutrient solutions, roots, microbes, plant pathogens, insects if pollination requires them, and a larger network of living processes. A crop system provides oxygen support, fresh food, psychological value, and partial nutrient recycling. It also provides new failure modes. A fungal outbreak can damage plants. A nutrient imbalance can reduce yield. A mutation or microbial contaminant can spread through genetically similar crops. A lighting failure can become a food emergency. Agricultural chemicals must be controlled in the same sealed atmosphere the crew breathes. The ship needs biodiversity for resilience, but biodiversity increases complexity. Monocultures are efficient and predictable until one disease affects the entire crop. Diverse crops provide redundancy but demand more space, expertise, storage, and environmental control. The agricultural system must survive crew turnover, equipment failure, and mistakes by people who may not have been born when it was designed. Food, immunity, and psychology meet in the same compartment. A failing crop changes nutrition. Reduced dietary variety affects the microbiome. Poor nutrition weakens recovery. The loss of plants removes one of the few living environments available to the crew. Morale declines. Stress rises. Sleep worsens. Immune regulation shifts again. The greenhouse is not decoration. It is part of the medical system. By year 20, the crew may know the ship's microbial landscape as well as engineers know its wiring. They may maintain maps of persistent biofilms, track genetic changes in bacterial populations, adjust diet to support individual microbiomes, and preserve samples from earlier years as biological reference points. They may also discover organisms behaving in ways no launch-era model predicted. This is not because space creates monsters. It is because evolution never stops. 40 years is a short interval for a human institution and a long interval for microbes. Bacteria can pass through thousands of generations. Mutations arise, selection acts, populations exchange genes. The environment rewards whatever survives its disinfectants, radiation, nutrient patterns, and temperature cycles. The crew ages by decades. The microbes age by evolutionary time. The ship must therefore maintain an uneasy balance. It must remain biologically rich enough to support human health and controlled enough to prevent that biology from overwhelming its systems. It must use antibiotics without exhausting them, disinfect surfaces without destabilizing the habitat, grow food without importing an uncontrollable ecological burden, and interpret immune changes without terrestrials' medical certainty. The first infection may be treated successfully. The 10th may require a drug no longer potent. The 100th may involve an organism the original diagnostic system misidentifies. And every illness occurs inside a crew already carrying the effects of radiation, altered gravity, fatigue, aging, and limited reserve. The sealed microbial world does not need to defeat the crew by itself. It only needs to arrive when the crew has less left to fight with. A 40-year mission carries a population through time, not merely through space. At departure, the crew may be selected from healthy adults in the strongest years of their working lives. Their cardiovascular systems are robust. Their bones and muscles begin above average. Their medical histories are carefully screened. Their technical skills overlap so that no single illness immediately removes a critical capability. 4 decades later, none of those assumptions remain intact. Even in the best possible habitat, the crew will age. The question is not whether aging occurs in space, but how ordinary aging interacts with radiation, altered gravity, confinement, disrupted sleep, limited medicines, and decades of accumulated exposure. Aging on Earth is already a systems problem. Bone remodeling shifts. Muscle mass becomes harder to preserve. Blood vessels stiffen. Immune regulation changes. Cancer risk rises. Vision and hearing decline. Recovery from injury slows. Sleep becomes more fragmented. The brain often retains deep knowledge and judgment while losing some speed, flexibility, or reserve. Modern society surrounds that process with support. Medical screening becomes more frequent. Prescriptions change. Joint replacements restore mobility. Cataracts are treated. Cardiac conditions are monitored. Cancers are detected and managed with specialized tools. Families and institutions redistribute physical work. A starship must provide all of that inside one vehicle, while its own support systems are aging too. The crew and the ship deteriorate on parallel timelines. The exercise machine protecting bone density develops wear. At the same time, the astronauts become less able to tolerate missed training. The medical scanner loses calibration as the probability of serious disease rises. The oldest crew members need more pharmaceutical support precisely when stored medications spent the longest time exposed to heat cycles, radiation, and packaging degradation. The mission becomes most medically demanding when its equipment is least new. That overlap may be more dangerous than any single biological effect. A 35-year-old crew member can recover from an injury that might permanently disable the same person at 70. A brief loss of artificial gravity in the early mission may produce limited harm. The same failure in year 35 could act on bones, muscles, and cardiovascular systems already weakened by age and previous exposure. The ship does not need to lose gravity for years. It may only need to lose it at the wrong time. Redundancy helps, but redundancy also ages. Identical components built together may contain identical weaknesses. Replacement units stored for decades can degrade even without operating. Lubricants separate, polymers become brittle, radiation affects electronics, seals change shape. Data describing old components may remain available while the materials needed to repair them have been consumed. A crew entering old age is therefore depending on a machine entering old age. The usual response is maintenance, inspect constantly, replace components before failure, manufacture parts on board, redesign systems during the voyage, preserve raw materials rather than carrying every finished spare, use modular hardware that can be opened, understood, and rebuilt by the crew. This improves mechanical resilience. It also increases dependence on human labor. Maintenance consumes time, attention, dexterity, vision, strength, and judgment. It assumes the crew can enter confined spaces, manipulate tools, interpret unusual wear, and improvise safely. The same people experiencing biological decline are responsible for preventing mechanical decline from accelerating. The work required to preserve the habitat may gradually exceed the crew's ability to perform it. At first, tasks can be redistributed. Younger or healthier members take more physical work. Automation handles inspections. Robotic systems enter dangerous spaces. Procedures are simplified. But a 40-year mission with one launch generation contains no younger adults unless children are born aboard. That decision changes the voyage completely. Without reproduction, the crew is a closed population aging toward the destination. The mission must arrive before too many essential capabilities are lost. Departure age becomes a design parameter. Send very young adults, and the crew gains more biological time but may lack experience. Send older specialists, and the mission gains expertise but shortens the healthy working period available after arrival. No selection strategy eliminates the arithmetic. If the transit lasts 40 years, every adult arrives 40 years older. The ship may carry more crew than operations require, so that illness and aging do not remove entire specialties. Yet every additional person increases food, water, habitat volume, medical demand, radiation shielding, and life support load. A larger crew provides redundancy in skill and genetics, but makes the vehicle heavier and more complex. Once again, biological protection enlarges the propulsion problem. Reproduction appears to offer another path. Children born during the voyage could reach adulthood before arrival. They could take over maintenance, preserve physical labor capacity, and extend the mission beyond the lifespan of the original crew. But reproduction is not a staffing mechanism. It is the creation of human lives inside an experiment whose most important biological conditions remain poorly understood. No human pregnancy has been completed in space. No child has developed from conception to adulthood in microgravity, partial gravity, or the radiation environment beyond Earth's magnetic protection. Animal research provides clues, but it does not establish that human reproduction and development would proceed safely across an interstellar voyage. Pregnancy reorganizes nearly every major system in the body. Blood volume rises, cardiovascular demand changes, bone and mineral metabolism shift. The immune system enters a carefully regulated state that permits fetal development while still protecting the mother. Hormones alter tissue, sleep, temperature control, and metabolism. Spaceflight changes many of those same systems. The interaction is not known. Radiation creates an especially severe concern because developing tissues divide rapidly. The embryo and fetus build organs through sequences of growth, migration, specialization, and structural change. Damage during a critical developmental period can have consequences unlike the same exposure in a mature adult. Shielding could reduce the risk, but pregnancy may require the safest region of the ship for months. That region must also serve as a solar storm shelter, medical center, or command space. Water, food, and structural mass may need to be arranged around it permanently. A reproductive program therefore changes the geometry of the spacecraft. Gravity would be equally important. Adult bodies lose tissue when normal loading disappears. A developing body is constructing tissue for the first time. The skeleton is not merely being maintained. Its shape, internal architecture, and strength are emerging in response to mechanical conditions. A child raised in partial gravity might develop normally for that environment and still be unable to tolerate Earth gravity or the gravity of the destination. The cardiovascular system would also mature under a different pressure gradient. Balance and orientation would develop without the same reference that shaped every human nervous system on Earth. Muscles would learn to control a body whose weight might be a fraction of what its mass would produce on a planet. These differences might be manageable adaptations. They might also impose permanent limitations. The first generation born aboard would reveal the answer, but only after the decision had become irreversible. Their development would affect mission operations long before adulthood. Children require nutrition that changes with age, education, medical monitoring, privacy, exercise, psychological support, and protection from hazards designed around trained adults. Equipment must be adjustable. Spaces must accommodate different body sizes. Emergency procedures must include people who cannot perform technical roles. The ship would no longer be a workplace carrying specialists. It would be a society. That society would face a moral problem the launch crew did not. The adults chose the mission. The children did not. They would inherit a destination selected before their birth, a closed environment they cannot leave, and responsibilities they did not accept. The mission may need them to become engineers, physicians, biologists, and pilots, regardless of their interests. Their education would be shaped by the survival requirements of the ship. Personal freedom would exist inside a system that cannot permit every possible choice. If a child refuses the technical role assigned by demographic planning, the conflict is not only cultural. It may threaten the maintenance of life support. If several members of the next generation reject the mission's destination, there is no alternate settlement and no return path. A starship that reproduces must preserve consent, social stability, and technical continuity without the ordinary safety valve of departure. That may be harder than preserving air pressure. The crew also has to manage population size. Too few births produce an aging community without enough replacements. Too many strain food, habitat, medicine, and education. Infertility, miscarriage, illness, or an uneven distribution of skills can disrupt plans made decades earlier. Genetic diversity matters if the mission continues across generations, but the required population cannot be reduced to one universal number. It depends on mission duration, reproductive planning, stored genetic material, medical technology, and how much risk the designers accept. A crew large enough to create a stable society is far larger than a crew needed merely to operate a vehicle. The habitat begins approaching the scale of a settlement. Agriculture expands. Manufacturing becomes more complete. Governance becomes unavoidable. The mission needs rules for reproduction, medical decisions, resource allocation, education, leadership succession, privacy, conflict, and the treatment of people who cannot contribute equally. These are not secondary issues to be solved after the propulsion system works. They determine whether the biological mission survives long enough for propulsion to matter. By year 30, The original crew may still hold formal authority, while younger members carry much of the physical workload. Experience and strength are divided between generations. Earth is a place known directly by some and only through recordings by others. The destination means different things to each group. For the launch crew, it is the purpose of a lifetime. For those born aboard, it may be an inherited obligation. The ship can remain mechanically sound while that difference grows into a political fracture. And if the mission does not include children, the alternative is not simple. The original crew must arrive old enough that every landing, repair, medical emergency, and surface operation is performed by people who have already spent decades under biological stress. Either design carries a failure threshold. One risks developmental biology and social continuity. The other risks arriving with no healthy generation left to complete the work. The question of what fails first has now expanded beyond the body of a single astronaut. It includes the population structure of the entire mission. A starship can preserve individuals for a time. To preserve human capability for 40 years, it may have to preserve a civilization. A civilization aboard a starship would still depend on a machine. That machine would not remain unchanged for 40 years. Every pressure vessel, pump, bearing, cable, seal, radiator, valve, sensor, and processor begins aging the moment the mission starts. Some components wear through use. Others degrade while sitting still. Radiation alters electronics. Temperature cycles stress materials. Lubricants migrate. Polymers lose flexibility. Microscopic cracks grow. Calibration shifts. The spacecraft is not a permanent shelter. It is a structure continuously negotiating with failure. On Earth, complex machines survive because they belong to industrial systems larger than themselves. Aircraft return to maintenance facilities. Power plants receive replacement parts from factories. Hospitals depend on manufacturers, laboratories, and supply chains. Even remote research stations can request equipment from outside. An interstellar ship has no outside. Its ability to remain habitable depends on how much of the industrial world can be compressed into the vehicle. Tools, raw materials, manufacturing systems, inspection equipment, repair knowledge, and enough energy to use them. The problem is not simply carrying spares. A mission lasting decades cannot predict every component that will fail. Carry too many finished replacements, and mass rises rapidly. Carry too few, and one unanticipated failure can disable a critical system. The more efficient strategy is to carry standardized parts, adaptable machines, and the raw material needed to manufacture replacements on board. That moves the risk from inventory to production. A manufacturing system must itself be maintained. Its tolerances must remain precise. Feedstock must stay usable. Software must be understood. The crew must be able to test whether a replacement is strong enough for the load it will carry. A part that fits is not necessarily a part that can survive. In a pressure system, a hidden flaw can become a leak. In a rotating habitat, a poorly manufactured component can fail under repeated stress. In a medical device, a small calibration error can alter diagnosis or treatment. The ship must therefore preserve measurement as carefully as it preserves machinery. Reference instruments are needed to verify other instruments. Those references also drift. Standards must be compared against systems designed to remain stable across time. The farther the mission moves from launch, the more its definition of accuracy depends on an internal chain of trust. If that chain weakens, the crew may be repairing the ship with tools that no longer tell the truth. Biology depends on those measurements. Atmospheric composition must remain within narrow ranges. Oxygen, carbon dioxide, humidity, pressure, and trace contaminants affect cognition, sleep, cardiovascular function, and long-term health. Water quality must be monitored for chemicals and microbes. Food production depends on nutrient concentrations, lighting, temperature, and gas exchange. Medical systems depend on sensors whose errors may look like changes in the patient. A drifting instrument can create a biological failure without any visible mechanical breakdown. Suppose a carbon dioxide sensor begins reading slightly low. The life support system responds to the number it receives, not the atmosphere the crew actually breathes. Concentrations rise slowly. The crew experiences headaches, poor sleep, reduced concentration, and irritability. Those symptoms resemble fatigue, stress, aging, or infection. The people interpreting the problem are affected by the problem. They may blame one another before they question the sensor. This is how a technical fault becomes a social and cognitive fault at the same time. Closed-loop life support is especially vulnerable to interactions. A starship must recover water, manage waste, at least generate air, and produce at least part of its food. Each loop improves self-sufficiency. Each also connects systems that might otherwise fail independently. Waste becomes agricultural input. Agriculture influences air composition. Water treatment supports both crew and crops. Microbial processes help recycle nutrients. Power loss affects pumps, lighting, heating, and filtration together. Efficiency creates coupling. Coupling creates the possibility of cascades. On Earth, a failed crop does not usually damage the atmosphere inside a person's home. On a ship, it might. A plant disease reduces food production and carbon dioxide uptake. The crew increases reliance on stored food. Waste composition changes. Nutrient recycling becomes less balanced. The air system works harder. Power consumption rises. One biological disturbance propagates through engineering. The reverse is equally true. A cooling failure changes greenhouse temperature. Plants become stressed. Fungal growth increases. Crop yield falls. The crew loses fresh food and part of its psychological refuge at the same time. The vessel is not carrying separate systems. It is carrying one metabolism built from machines, microbes, plants, and people. The closest terrestrial analogy is not a vehicle. It is an ecosystem under constant maintenance. Natural ecosystems absorb disturbance through scale and diversity. If one species declines, another may occupy part of its role. If one region experiences drought, another remains productive. Energy and nutrients move through networks with enormous redundancy. A starship ecosystem is smaller, more efficient, and more fragile. Every organism aboard was selected. Every habitat volume is constrained. Every resource flow is managed. That control improves predictability, but it reduces the unplanned diversity that makes natural systems resilient. The ship cannot carry a forest, a watershed, and an atmosphere deep enough to absorb years of error. It carries narrow substitutes. The crew can add redundancy, but redundancy requires space and mass. Multiple crop species reduce agricultural risk but increase operational complexity. Parallel water treatment systems improve reliability, but consume power and maintenance. Larger atmospheric reserves buffer faults, but require a larger pressure vessel. The safest ship is not the lightest ship. The lightest ship is easier to accelerate. Every design decision returns to the same conflict between speed and survival. A faster spacecraft reduces mission duration. Fewer years mean less radiation exposure, less aging, fewer maintenance cycles, and fewer opportunities for disease. Speed is therefore a biological countermeasure. But speed has its own biological cost through engineering. More propulsion energy may require more fuel, larger radiators, stronger structures, or more dangerous power systems. High velocity increases the energy of collisions with dust. Greater shielding may be needed around critical areas. Acceleration and braking must remain tolerable for the crew and the rotating habitat. If achieving higher speed forces designers to reduce shielding, medical capability, habitat volume, or system redundancy, the shorter voyage may not be safer. A slower, heavier ship might protect the crew better each day while exposing them for many more days. There may be no clean optimum. The answer depends on technologies that do not yet exist and biological thresholds that have not been measured. The crew will live inside that uncertainty. By the fourth decade, maintenance will shape daily life more than exploration. The destination may be visible, but most labor will still be devoted to preserving the conditions required to reach it. Inspections, replacements, software verification, crop management, medical monitoring, and exercise will consume the schedule. The voyage will not feel like moving through space. It will feel like keeping a world from shrinking. Every irreversible loss makes that world smaller. A failed laboratory reduces diagnostic capability. A damaged greenhouse narrows the diet. An exhausted chemical reserve removes one method of water treatment. The death or disability of a specialist removes knowledge that may exist in records but not in practiced hands. The ship can remain operational while its range of possible responses steadily contracts. This is another form of declining reserve. At launch, a problem may have 5 solutions. In year 30, it may have 2. Near arrival, it may have 1. A system with 1 remaining solution can still look functional. It may perform every normal task. But it has lost resilience since the next failure does not need to be severe. It only needs to remove the final path. The crew's biology follows the same pattern. A healthy person can tolerate infection, missed sleep, stress, and injury because multiple systems compensate. As those systems weaken, normal disturbances become dangerous. The ship and the crew are becoming alike. Both are collections of aging subsystems. Both survive by compensation. Both can appear stable after their safety margin has nearly disappeared. The first decisive failure may occur when those 2 declining reserves meet. An aging crew faces a repair that requires strength, vision, judgment, and uninterrupted work. The repair protects a system supporting air, water, gravity, or food. The task is possible for the people who launched. It may no longer be possible for the people who remain. At that moment, the spacecraft will not have failed before the crew. The crew will not have failed before the spacecraft. They will fail as one system. Arrival begins years before the destination is reached. A starship moving at a meaningful fraction of the speed of light cannot wait until the target system fills the window before deciding how to stop. Braking may require a propulsion system as demanding as the one used to accelerate. Navigation must account for measurements gathered decades after launch. The destination may contain planets, dust, magnetic fields, and radiation conditions that were only partly known when the mission began. The crew must prepare for the most complex phase of the voyage while carrying the accumulated damage of everything that came before it. This is where what fails first finally becomes practical. During cruise, many impairments can be hidden inside routine. The ship follows a stable trajectory. Automated systems perform repeated tasks. Physical demands are controlled. A crew member with reduced strength can avoid heavy work. A person with declining vision can use enlarged displays. A team with strained relationships can divide responsibilities and limit contact. Arrival removes those accommodations. The ship must change state. Propulsion systems that have been quiet may need to operate at full capacity. Sensors must distinguish planets from background sources. The crew must interpret unfamiliar data without immediate confirmation from Earth. Course corrections become more consequential. A mistake that once produced a small deviation can now determine whether the vessel enters the system, misses it, or approaches an object at an unsafe velocity. The destination is not a finish line. It is an emergency room, construction site, observatory, and landing operation combined. If the mission plans to remain in space and study the system remotely, the crew still needs reliable instruments, stable power, functioning communications, and the cognitive ability to decide where limited time and fuel should be spent. If the mission plans to enter orbit, deploy probes, or land, the physical demands rise sharply. A planetary surface introduces gravity, terrain, dust, weather if an atmosphere exists, and conditions that may differ from every assumption made before departure. Even a world with gravity similar to Earth would not feel familiar to bodies that have spent decades in artificial or reduced gravity. Standing is only the beginning. The crew must carry equipment, climb, recover from falls, work in suits, and respond to unexpected loads. Their cardiovascular systems must tolerate sustained upright activity. Their bones must withstand impact. Their muscles must provide more than enough strength for ordinary movement because exploration rarely occurs under ordinary conditions. A person who can walk across a medical testing area may still be unable to rescue another crew member, repair a damaged lander, or return to shelter before a life support limit expires. Functional survival is stricter than clinical survival. This is why no single measure can define whether the crew is ready. Bone density alone is insufficient. Muscle strength alone is insufficient. Cognitive testing, immune markers, radiation dose, visual acuity, and cardiovascular performance each describe only one part of the system. The mission succeeds only if enough parts remain above their operational thresholds at the same time. That condition may fail first in the person with the worst individual response. Human biology varies widely. Two crew members exposed to the same environment may lose different amounts of bone, experience different visual changes, respond differently to radiation, and age along different trajectories. Selection can reduce known risks. It cannot remove variation. A crew chosen from the healthiest available population may still contain one person whose body reacts unexpectedly after 10 years, another whose sleep deteriorates after 20, and another who remains physically capable but develops a cancer near arrival. The mission must be designed for the distribution, not the average. Average performance can look acceptable while one critical specialist crosses a threshold. Redundancy in training helps. Every essential skill should belong to several crew members, but deep expertise is difficult to duplicate. A propulsion specialist can teach procedures, yet decades of intuition about a specific system may remain concentrated in one person. A physician can distribute medical knowledge, but experience under pressure cannot be copied into a manual. The first failure may therefore be the loss of one irreplaceable combination of knowledge and capacity. The crew member is alive. The knowledge still exists, but the body can no longer deliver it when needed. Automation may appear to solve this. Advanced systems could control braking, identify hazards, manage navigation, diagnose illness, and coordinate repairs. For an interstellar mission, extensive autonomy is unavoidable because Earth cannot participate in real time. But autonomy changes the nature of human responsibility rather than eliminating it. When automated systems work correctly, the crew becomes less practiced at direct control. When they fail, the people must intervene in the exact situation for which practice has been weakest. This is a familiar problem in aviation and other highly automated fields, but the interstellar version is amplified by decades. A crew may spend most of its adult life supervising systems that rarely require manual correction. Then, during arrival, a sensor conflict forces them to reconstruct the ship's true state from incomplete information. Their ability to do that depends on memory, training, documentation, interface design, trust, and the physical condition of the people involved. If the software has been updated repeatedly during the voyage, the system may no longer behave exactly as it did in launch simulations. If repairs replaced original components with improvised versions, performance models may contain assumptions that are no longer true. If sensors have drifted, the data may disagree for reasons that cannot be resolved quickly. The crew is no longer operating the ship that left Earth. It is operating the ship that survived. That distinction matters. The vessel near arrival contains repaired structures, changed software, redistributed shielding, depleted inventories, modified routines, and a crew adapted to decades of compromise. The mission plan may have been revised hundreds of times. Every revision was rational when made. Together, they may have created a vehicle whose final behavior no original model fully represents. This is the accumulated cost of survival. It does not imply negligence. It is what long-duration resilience looks like in practice. Systems are altered to keep them working. Resources are redirected to protect immediate needs. Procedures evolve around the people available. The mission becomes increasingly specific to its own history. Arrival then asks this unique aging system to perform a sequence designed before that history existed. The safest response is to avoid a single decisive arrival event. Send autonomous probes ahead. Begin observations years before the main vessel enters the system. Map dust, radiation, planetary atmospheres, and potential landing sites. Preserve multiple trajectories. Keep the crew in the most protected environment while machines take the first risks. This reduces uncertainty. It does not remove the need for capable humans. The crew must interpret what the probes find. They must decide whether the original destination remains viable. A planet believed to be suitable may have an atmosphere too thin, a surface too active, or radiation conditions too severe for settlement. The best orbit may require more fuel than expected. A seemingly minor hazard may force the mission to choose between scientific value and survival. The people making that decision cannot ask Earth what to do. A message home will arrive years later. Any answer will return years after that. The crew is the final authority because distance has made every external authority irrelevant to the immediate problem. This is the ultimate consequence of interstellar travel. The mission begins as an engineering project created by a civilization. It arrives as an isolated civilization, forced to judge the work of its founders. By then, some launch-era assumptions will be outdated. Some scientific questions will have changed. Some crew members may no longer believe the original objective justifies the remaining risk. Others may see completion as the only meaning capable of holding the community together. The final conflict may not be between the crew and the environment. It may be between different definitions of success. One group may favor a conservative orbit and remote study. Another may argue that 40 years of sacrifice are meaningless without landing. A younger generation may reject a surface selected before they were born. The oldest members may feel responsible for completing the promise they made at departure. No technical checklist can settle that disagreement. Governance becomes part of navigation. If trust has survived, the crew can weigh evidence, uncertainty, and human cost. If trust has degraded, the arrival decision can divide the ship at the moment unity matters most. This is why the first thing to fail on a 40-year mission may not be bone, muscle, vision, immunity, machinery, or medicine. It may be reserve. The reserve that allows a body to recover. The reserve that allows a machine to tolerate one more fault. The reserve that allows a crew to disagree without fragmenting. The reserve that allows a civilization to choose caution after spending a lifetime pursuing a destination. Every hazard of the voyage consumes some portion of that capacity. Exercise restores part of it. Shielding preserves part of it. Redundancy, medicine, automation, and social design protect part of it. None makes it infinite. Near the target star, the crew may still be alive, the ship still pressurized, and every major system still functioning. Yet the mission may possess no safe response to the next unexpected event. That is the threshold that matters, not the moment something stops working. The moment nothing else remains capable of compensating when it does. The braking burn begins with no applause. For 40 years, the crew has lived inside a machine built to delay failure. Every repaired valve, every medical decision, every protected hour of sleep, every exercise session, every argument resolved without fracture has purchased this moment. The destination star no longer resembles the point of light that guided the early voyage. It has become a source of heat, radiation, gravity, and decisions. Its planets move against the background. Dust registers on forward sensors. Autonomous probes return measurements from places no human has seen directly. The ship has reached another system. That does not mean the mission has succeeded. The propulsion system must reduce a velocity accumulated decades earlier. The habitat must tolerate changes in acceleration and rotation. The power network must support instruments, navigation, communication, medicine, and life support during the most demanding operations of the voyage. The crew must do the same. Some walk more slowly than they did at departure. Some depend on medication that did not exist in the original mission plan. Their muscles and cardiovascular systems have been protected as well as the ship could protect them, but protection is not preservation without loss. Their eyes, immune systems, bones, sleep, and cognitive reserve each carry a different history. They are not the crew selected on Earth. They are the crew the voyage produced. The first question was what would fail first on a 40-year mission to another star. The evidence does not point to one universal answer. A poorly shielded vessel might lose crew health to radiation before anything else becomes decisive. A ship without effective gravity could arrive with severe musculoskeletal and cardiovascular limitations. A small crew might be broken by illness, conflict, or the loss of one essential specialist. A highly complex habitat might survive biologically only to become impossible to maintain. A generation mission could preserve physical labor while creating social and developmental risks no short mission has ever tested. Different designs move the first failure to different places. That is not the same as removing it. Every countermeasure protects one reserve while consuming another. Shielding preserves tissue but adds mass. Artificial gravity protects several body systems but requires structure and maintenance. A larger crew provides skill redundancy but increases life support demand. More medical capability reduces dependence on Earth but expands the machinery the crew must sustain. Faster travel shortens exposure but raises propulsion and impact challenges. The mission is not choosing between safety and danger. It is choosing where danger will be stored. The most important design decision may therefore be the amount of margin carried across the voyage. Not only extra oxygen, spare components, or redundant computers, but biological and social margin. Enough strength to recover from an injury, enough pharmaceutical capacity to treat an unexpected disease, enough trained people to absorb the loss of a specialist, enough trust to survive disagreement, enough power and raw material to solve a problem the original designers failed to imagine. Margin is expensive because it looks unused until the moment it becomes the mission. A spare pump may remain untouched for 30 years. An additional physician may appear unnecessary through decades of good health. A heavily shielded room may stand empty between solar events. A second crop system may seem inefficient while the first one thrives. Then one failure occurs, and the supposedly unused capacity becomes the only reason the voyage continues. This is why a true interstellar ship would not resemble the elegant vehicles of popular imagination. It would be less like an aircraft and more like a moving settlement carrying its own medical system, industrial base, ecology, archive, government, and emergency reserve. Its mass would reflect everything human biology cannot do without. Its internal design would reveal the real nature of the journey. The largest protected volume might not surround the engines or the command deck, but the living spaces. Water and supplies would be arranged around the crew as shielding. Gravity would be treated as medical infrastructure. The greenhouse would be part of the food, air, microbial, and psychological systems at once. Manufacturing would serve both machinery and medicine. Education would be a survival function if the mission crossed generations. The people would not be cargo inside the vehicle. They would be the reason for nearly every difficult feature of it. This does not make human interstellar travel impossible. It makes the word possible more demanding. A propulsion concept can be physically possible while the mission remains biologically incomplete. A habitat can be engineered in principle while its reproductive assumptions remain untested. A radiation model can reduce estimated dose without proving that human cognition will remain intact across decades. An autonomous medical system can diagnose known disease while remaining unprepared for physiology created by a lifetime in space. The necessary technologies do not all mature on the same schedule. Propulsion may advance faster than radiation biology. Artificial gravity may be demonstrated before long-duration reproduction is understood. Autonomous probes may reach nearby stars long before physicians know how to preserve a crew for the same trip. That sequence may determine how exploration actually unfolds. Machines are likely to go first because information can cross distances that bodies cannot yet tolerate. Small probes can map dust, magnetic fields, planets, atmospheres, and radiation conditions. Their data can replace imagination with measurements. Later missions can be designed around an environment that is partly known rather than almost entirely inferred. Human presence, if it follows, will depend on lessons gathered much closer to home. Long stays in orbit can reveal how countermeasures perform across years rather than months. Lunar habitats can test sustained life in partial gravity. Mars missions can expose crews to long communication delays, surface gravity, deep space radiation, and medical isolation on a scale no current mission has combined. Each step will identify problems that no model predicted. That is not failure. It is the purpose of proceeding in steps. The most dangerous interstellar mission would be one designed by a civilization that believed determination could substitute for missing evidence. Courage matters after the risks are understood. It cannot supply a gravity threshold no experiment has measured. It cannot reverse radiation damage that shielding failed to prevent. It cannot make an aging medical system produce a treatment it was never built to manufacture. The honest path to the stars is slower than the dream. It begins by treating the human body with the same seriousness given to engines and trajectories. It requires experiments that may take generations. It requires mission planners to admit where extrapolation ends and ignorance begins. It requires building settlements near Earth that can fail safely enough for humanity to learn from them. Most of all, it requires changing what arrival means. The first crew to reach another star should not be judged only by whether their ship enters the system. They must remain capable of choosing what to do next. They must still possess the physical strength, medical reserve, technical competence, and social coherence to encounter conditions no one predicted. The voyage has not succeeded if the crew survives only as passengers inside an automated machine. It succeeds if they arrive as decision makers. Now the braking burn is nearly complete. The rotating habitat continues its slow movement. Pumps circulate water through lines repaired many times. Plants grow beneath lamps descended from systems designed on a planet 4 light-years behind them. The crew watches a new sun through instruments built by people who may no longer be alive. No recovery team waits outside. No hospital stands below. There is only the ship, the people it managed to preserve, and the world they have kept functioning between the stars. A warning sounds as the gravity changes. One crew member releases a handhold and places both feet against the floor. The test is no longer whether the starship can stop. It is whether the human being inside it can stand.